We're surrounded by all this amazing technology. Our entire lives are sitting on these tiny chips of silicon and metal. But have you ever really stopped to wonder how it all works? How does a chunk of metal understand a photo or your favorite song or even just the words you're seeing right now? Well, today we're going to crack the code on the secret language that makes it all possible. So yeah, that's the big question, right? How does a machine that can't see or hear or feel, how does it even begin to comprehend our incredibly rich and complex world? And the answer? Well, it's actually shockingly simple, but also kind of brilliant. The secret is to just simplify everything, radically. A computer takes our world of infinite variety, every single photo, song, and word, and it boils it all down into a language that has only 2 words. It's like having a conversation where you can only say yes or no, but you can say it millions of times a second. And this is the absolute core of it. At the most basic fundamental level, a computer is just billions and billions of tiny little light switches. Each one can either be on or it can be off. And we just represent that state with a 1 for on and a 0 for off. That's it. That's the entire vocabulary the computer has to work with. And this system, this language of ones and zeros, it has a name, of course. It's called binary. It's the native language of every single digital device on the planet. It's not even really a programming language. It's the bedrock that everything else is built on. It's literally raw electricity, speaking. Okay, so you're probably thinking, how on earth can just 2 numbers represent, well, everything? How do you get from a simple on and off to the number 58, or the color red? The magic isn't really in the 2 digits themselves. It's all about how you arrange them in long, long sequences. So let's try it. Let's translate our number, 58, into computer speak. And don't worry, the process is way simpler than you'd think. It's just a simple game of dividing by 2 over and over again and writing down if there's a remainder. See, the computer doesn't care about the idea of 58. It just needs a series of yes-no answers. Was there a remainder or not? And when you take those remainders and read them from the bottom up, our number 58 turns into this binary string, 111010. For the computer, that's just a specific set of switches, on, off, on, off. That unique sequence is how it knows we're talking about 58. Okay, so this system is absolutely perfect for a machine. It can read billions of these on-off states every single second. But for us, for the actual humans who have to write the code and fix the bugs, well, that's where we hit a snag. Reading these giant strings of ones and zeros is a recipe for a massive headache. And this is where the problem becomes crystal clear. Look at that. That giant unreadable string of 24 ones, that's the binary code for the color white. Seriously, could you imagine trying to spot a typo in that? Is that 23 ones or 24? No way. It's just not practical for people to work with. So this led to a really important question for all the early programmers and engineers. How can we create a shorthand, a way to represent these long binary strings that's more compact and easier for our human brains to handle without actually changing the language the computer understands? And the answer they came up with is called hexadecimal. If binary is the computer's native language, you can think of hexadecimal as our human-friendly cheat sheet. It's a system that's designed to take those long, messy binary strings and package them into these short, tidy bundles that are much, much easier for us to work with. The trick behind hex, as they call it, is that it uses a base of 16 instead of just 2. So you've got our normal numbers, 0 through 9, but then you need 6 more symbols to get to 16. And what did they do? Super simple. They just borrowed the first 6 letters of the alphabet, A, B, C, D, E, and F. That simple little trick is the key to all of its power. The translation process is pretty much the same idea, but this time, instead of dividing by 2, we divide by 16. So let's take a bigger number, like 759. You do a couple of quick divisions, and boom, that 3-digit number becomes the super short and sweet hex value 2F7. See how much cleaner that is? And right here, this is the real aha moment. Remember that absolutely ridiculous, monstrous binary string for the color white? Get this. In hexadecimal, it's just #FFFFF. 6 characters. That's it. Simple, elegant, and if you've ever dabbled in web design or digital art, you have definitely seen that before. Yeah, that's what we call a hex code. And seriously, anytime you see that little pound sign or hashtag followed by 6 characters to define a color online or in a program, that's it. That's hexadecimal right there in your daily life. It's the perfect example of a system made not for the computer, but for the humans who need to talk to it. So, when you boil it all down, you've really got these 2 essential languages. You've got binary, that's the computer's native tongue, the raw on-off pulses of electricity. And then you have hexadecimal, that's our Rosetta Stone. It's the clever translator we built so we could talk to the machine without going completely crazy. You know, it's actually a pretty amazing partnership when you think about it. Our huge, colorful, noisy world gets translated down into a simple on and off for the machine to understand, and then it gets translated back up into a neat shorthand so we can understand it. It really makes you wonder, what other complex things in our lives are just simple conversations if only we had the right translator to hear them? Thanks for joining me.